Okay, so we start working on Unit 3 practice exam, and we start with the multiple choice. Okay, so, and I think in the multiple choice we have a really good example of everything that you need. Okay, so, and yeah, we will try to cover. Just in case if you have any question, you can turn on your microphone or you can just type in the chat. I will just check, the chat while I'm just working on the problem. Okay, so if you have any question, please, don't hesitate, okay, to put your question in the chat or turn on your microphone, okay, and ask your question. So let me just bring the equation sheet as well. Okay, so I would like to have the equation sheet available here. Okay. Physics. There you go. Let me just see. Okay, so it's not here. Okay, let me just download the equation sheet. Are Okay, the equation sheet available in the right side. Okay, Unit 3 chapter. Okay, we have frequency, period, the velocity of the wave. Okay, so these are the equations that we will use. Okay, so there are just a couple of equations. Okay, so, and then we start with question number 1. So it's telling that question number 1 is telling that what is the common Sorry. Okay. So a common source of wave motion is a wave pattern, vibrating object, harmonic object, region of a variable, high and low pressure, none of those. So the right answer for this question is, you can type in the chat if you know the answer already. Okay, so I will check the chat. Yeah, the right answer for this question is the vibrating object. Okay. Yes, the right answer for this question is a vibrating object. Okay, any vibration, okay, we can explain any vibration motion, okay, or any periodic motion, we can just, use a wave model to explain the, kinematic and dynamic of that motion. Question number 2, which of the following is not a transverse wave? So we have two form of wave, okay, we call it transverse wave and longitudinal wave. um, uh, Longitudinal wave, okay, and transverse wave, okay, they are two different form of wave that we have. So transverse wave, it's a wave that, the moving object, vibration is perpendicular in its motion in in a medium. But the longitudinal, okay, these two motion are in the same direction. So we know that the light and radio wave are transverse wave. So it means that its propagation, okay, which is horizontal, but its vibration is up and down. Okay, it means that the propagation of the wave and its motion to the medium, which is perpendicular, okay, so are perpendicular. But sound is an example of a longitudinal wave, okay, because let's say if you create a sound wave, so and the sound will propagate in a direction of the wave, so that's we call a longitudinal wave. So here, sound is not a transverse, okay, is a longitudinal wave. Question number 3. Okay, it's telling how many vibrations per second are associated with 101 megahertz. You know, vibration per second means frequency. As you can see, the frequency formula, is one vibration over time period. Or we can define this as a number of number of vibration over time. Or we can say one vibration over time period. Okay, so if we have a back and forth motion, okay, so the period time, it means that the length of time that it takes one complete motion happen, one back and forth motion happen. So we can just define the frequency like one vibration over the period time, or we can say the number of vibration over time. So how many vibrations per time are associated with 101 megahertz? So, and it's telling that vibration over time is these megahertz. So this is the definition of the frequency. And you should know that the mega means million. Okay, so it does have 1 and 60 in front. Okay, when we just say 100 megahertz, we can just write it 101 and 60 in front. Okay, which is gonna be hertz now. Okay, hertz means vibration over second. So what is the right answer now? Okay, which one is the right answer? The last one, okay, is the right answer. Number 4, if the frequency of a certain wave is 10 hertz, its period is, okay, look at the formula on the right. So it's telling that period T is equal 1 over frequency. We already have the frequency, which is 10 hertz, okay? So we just plug it here, 1 over, what is the frequency? 10 hertz. Okay, when we calculate this, is going to be 1 divided by 10 is going to be 0.1. 0.1 second. So the correct answer is going to be 0.1 second. Please type down your question, okay, if you have any question about any of these problems, okay? An object complete, okay, good. An object completes how many vibration? 20 vibration in how many second? 10 second. What is the frequency? You see, we just define the frequency. Frequency is number of vibration over time. Okay, I write frequency, vibration over time. How many vibration we had? 20 vibration. In how many seconds this vibration have? In 10 seconds. So it means that 20 divided by 10 is going to be 2 hertz. Okay, so this is how we can calculate the you know frequency. Again, the other formula of the frequency is number of vibration over time, and which we already have one, and we know that one complete vibration is happening in one time period. Question number Question number 6. No, 5. No, we did 5. Okay, question number 6. Question number 6. Wave interference occurs for water waves, light waves, sound waves. All of the above choices are correct. None of the above choices are correct. So, what do you think? Type in the chat. I okay, Nicholas. Oh, okay. Yeah, interference happen for light waves, which is the radio magnetism, electromagnetism frequencies, and it happen for mechanical waves as well, like sound waves. And we have a water waves. Okay, we call it mechanical wave. Okay, so interference, wave interference, it doesn't matter. Is a mechanical wave or is a radio wave, okay, or light waves, okay. It happen in all form of waves. So the right answer will be all the above choices are correct. Does anyone have a question about this problem? Okay, so this is called a law of interference. Okay, sometimes we call it principle, interference principle law. Doppler effects occurs when a source of sound move away from you, toward you, either toward you or away from you, in a circle around you. Doppler effect, okay, it's when the frequency is changing based on the source of wave moving or the observer moving or listener. Let's say if you create a sound source, okay, so if there is a source which is creating a sound, if you are moving toward to the sound source, you hear a higher pitch than when you are moving away. We say that when you are moving toward to the sound source, the frequency increase. While we are moving away from the sound source, the frequency decrease. Sometimes this happen other way. Okay, the listener stay still. The sound source moves toward to the listener or away from the listener. Again, frequency will change as well. Okay, so uh, this is called Doppler effect. Sometimes they explain it with the wavelengths. So when you are moving toward, to the sound source, while the frequency increase, okay, the wavelengths decrease. Okay, when you are moving away from the sound source, when the frequency, we know that the frequency decrease, but wavelengths increase. Okay, we can explain this way as well. Okay, we call this effect Doppler effect, and it's happened for light as well. Okay, so when you are moving toward to this light source or moving away from the light source, okay, its wavelengths and frequency will change. Okay, so we call this effect Doppler effect. So what is the right answer here then? Either toward you or away from you. Okay, question number 8. An observer on the ground hears a sonic boom, which is created by an airplane flying at a speed. Okay, so this question is asking when the sonic boom happened. So the sonic boom happened when the velocity of observer or listener is bigger than the velocity of the sound. We already know that the sound velocity in the room temperature is 243 or 245 meter per second. If observer could move with a velocity bigger than the velocity of sound, it's more likely to hear a sonic boom. Okay, let's say you are on the ground, there is an airplane, and this airplane is moving with a velocity bigger than the velocity of the sound. You will hear, sometimes you hear a boom. Okay, so it means that you are in an area that you could hear the sonic boom. Okay, so which one is the right answer here? Okay, the greater than the speed of sound. Number 9, the source of a sonic boom may or may not be a meter of may or may not be an emitter of sound, must itself be an emitter of sound, is not itself an emitter of sound. So the right answer is may or may not be emitter of sound. Okay, it doesn't mean that the source, okay, the source of the sonic boom, okay, so be emitter or not emitter. Okay, so okay. Question number 10. If waves, can you explain number 9 a little more? Yes, why not? Okay, so the source of sonic boom. Okay, again, airplane. Okay, airplane itself is, it can be the source of a sonic boom, and the person who is standing outside of airplane, okay, can be a source of a sonic boom as well. Okay, so yes, let me just the source of a boom can. So, for instance, one example I can provide for this. Okay, I just wanted to just explain it with an example. So, for instance, a supersonic bullet, okay, produces a sonic boom, even though it is not intentionally emitting sound. You know, a bullet, an airplane jet as well. Okay, so airplane jet, okay, so it is not source of sound. Okay, but it creates a sound. Okay, so, and the same thing, a superbolic, okay, produces sonic boom. However, it is not intentionally emitting the sound. Okay, I think this is a good example. So number 10. Okay, question number 10. If waves are going by at the same speed, the wave with the greatest period of oscillation is the wave that has a greatest frequency, amplitude, and wavelengths. So which one do you think? It's telling that if waves are going by the same speed, the wave with the highest period. So it means that if we have frequencies equal 1 over t, if we have the highest period, the frequency will be smaller, okay? Because the frequency and period are inversely related to each other. T is high, the period is high, frequency is low. And frequency and the wavelengths are inversely related to each other. So it means that if the frequency is low, okay, the wavelength is going to be high. So the right answer for this one will be the wavelengths. Again, the highest period time will have a smaller frequency. Okay, the smaller frequency can have a greatest wavelength. Number 11. A floating leaf oscillates up and down. See, oscillates up and down. To complete cycle, 1 second. There you go. This is the vibration frequency definition. Yes? Okay, so, and it's telling that if the wavelength is 10 meter, if the wavelength, lambda is wavelength, okay, lambda is wavelength, 10 meter, what is the speed? Okay, go back to the formula sheet, okay, you see that wave speed is equal to frequency multiplied by wavelengths. So I just write V equal frequency multiplied by lambda. Okay, what I need lambda, I need frequency to calculate the velocity. I already have lambda, which is given 10 meter, and I don't have frequency. But if I read the question, give me some information about vibration over time. Perfect. Frequency is going to be number of vibration, which is 2 complete vibration over 1 second. 1 second, there you go. It's going to be frequency is going to be 2 hertz. Okay, velocity is going to be 2 hertz multiplied by 10 meter. Hertz is 1 over second. Okay, so 2 times 10, it will be 20 meter per second. Yes, yeah, two oscillation happening in 1 second. That's how we can calculate the frequency. We just said that, frequency is number of vibration over time. How many vibration, complete vibration happen? Two complete vibration or cycle or motion or up and down motion happening in 1 second. We just use this formula, vibration, 2, how many second? 1 second. 2 over 1 is going to be 2 hertz frequency. And the velocity formula is frequency multiplied by lambda. 2 hertz times 10 meter is going to be 20 meter per second. Any question? This is how we can calculate the velocity. The velocity is frequency multiplied by lambda. Lambda is given, but we need to find the frequency from the equation. So the right answer for this question is going to be 20 meter per second. Okay, the frequency of the second hand on a clock is, okay, second hand. How many seconds it takes for the second hand to complete one vibration? We are talking about the minute one. Yeah, okay, minute. Okay, so it takes 60 seconds, yes, to complete one vibration. Again, we can calculate that. One vibration completed in 60 seconds. Okay, so we call it 1 over 60 hertz. Hertz. Number 13. For light, a redshift indicate that light source is moving. Okay, so you have if you read the textbook, okay, you see a redshift, blue shift. Redshift when the light source, so we use it for, light sources. Okay, so electromagnetism wave. Okay, so which the light source is one of those. So redshift when the source is moving away from you, and blue shift when the light source is moving toward you. Because we have a redshift here, redshift is going to be away from you. This is how we define. At this point, when the source is moving away, so the frequency will decrease, but the wavelengths will increase. Okay, so number 14, if you double the frequency, it's telling that if you double the frequency of vibrating, what happened to its period? We said that frequency and period are inversely related to each other. If you double the frequency, what happened to the period? The period will be half because it's inversely related to the frequency. Number 15. Okay, when you can explain 13 one more time. Okay, 13. Yeah, why not? Okay, so go back to 13. Okay, so let me just erase this. Okay, 13. Okay, is a definition of redshift and blue shift. So we talked about the Doppler effect. We said that Doppler effect, it is it happen when you have a mechanical wave or when you have electromagnetism wave. Light wave is a kind of electromagnetism wave. When you have let's say a star, there is a star, yes, good, and the star is radiating what? Light. If you are standing on the planet, okay, and if the star is moving toward you, is moving this way, is moving toward to the person, the frequency increase, but the wavelengths decrease. We call this blue shift. When you have a star, okay, is again radiating light. It can be visible light, infrared, X-ray, gamma ray, okay, any. If the star is moving away from you, good, the frequency decrease, the wavelengths increase. We call this shift red shift. Okay. Do you want me to explain more or? Okay, perfect. Nicholas, do you have any question? No, that's all right. No problem. Yeah, please ask questions. Okay, if you have any question, I am just tracking the chat. You can type down any question. I am okay to go back and explain everything 2 times, 3 times. Question number 15. Just letting you know that if you check these questions, we are doing the same calculation for different problems. The wording has changed a little bit, okay, but we are doing the same thing. For instance, in this question again, question number 15 is asking to calculate the speed of wave. Okay, S speed. What is the S speed? Frequency multiplied by lambda. If I have frequency, if I have lambda, okay, I can calculate the speed. Okay, let's see, I can find out these two from by reading the question. Okay, I start reading the question. A floating object oscillate up and down. Okay, I think we solved this, yes? No. Let's do it again. Okay. So up and down, two complete cycle in 1 second. Okay, this giving me the frequency definition. Frequency is gonna be number of vibration, two vibration in how many second? 1 second. So the frequency is 2 hertz. A water wave is how much? Okay, so lambda is given again 5 meter. That's it. I have frequency, I have lambda. Frequency is 2 times lambda. 5 is going to be 10 meter per second. The right answer is 10 meter per second. A, a skipper on a boat notices wave crest passing the anchor chain every 5 seconds. The skipper estimates the distance between the crest is 15 meter. Let me just draw the situation. Okay, so let's say this is a kind of wave, the water wave. Okay, so we call this crest, yes? These are trough. And it's telling that if the boat is here, the boat experiencing every of these crests, okay, from this crest to this crest, okay, it takes 5 seconds. Good. What is this 5 second? This is a period. T is 5 second. The distance, if you have a wave, displacement, okay, displacement over time, the distance from crest to crest, it is a one period. Good. If in a wave we have a displacement over position, okay, and in position, let's say we have this wave, the distance from crest to crest, okay, or two consecutive point, okay, is going to be lambda. So again, we can explain the wave, we can draw the wave with by x representation, position representation, with the time representation. With the position representation, we can find the lambda, the distance between two crests. If we have a wave which is with time, with respect to the time, the distance between two crests, okay, so it will give us the period. So here it's telling that from one crest to another crest, it takes 5 seconds. So it's going to be the period, 5 seconds. And it's telling that if the S keeper estimate the distance between the, okay, now the distance between two, which is lambda, 15, calculate the wave speed. Okay, what is the wave speed? Wave speed, again, frequency multiplied by lambda, okay? How can I find the frequency? Frequency is 1 over period, 1 over 5. So the frequency is going to be 0.2 hertz. There you go. I found the frequency. And I already have the lambda, which is given. The distance between two crests is going to be lambda, okay, which is lambda is 15 meter. So I just plug to this formula, 0.2 times 15, okay? When you multiply these two, 15 times 0.2 is going to be 3 meter per second. Any question about this problem? It's telling that we have a boat going from one crest to another crest, okay, or this boat experiencing crest by crest, okay, every 5 seconds. This gives me a period time. And it's telling that the distance between two crests, okay, is 15, which this is our lambda. We have lambda, we have frequency, we have a period. From period, we can calculate the frequency. When we have a frequency and lambda, we can calculate the velocity. So the right answer will be 3 meter per second. Question number 17. A jet traveling at 1500 kilometer per hour passes between observers A and B. In a short time, a sonic boom will be heard by observer A, observer B, and the pilot of the jet. Definitely the pilot of the jet cannot hear the sonic boom. Okay, is the pilot is the one who is moving with, the airplane. Yes? Good. So this is going to be wrong. Okay. Observer B, no. Okay. Both observer will hear that. Okay. What is the right answer? It's going to be just observer A and B. Definitely they will hear a sonic boom, but the pilot, which is inside the airplane and moving with the airplane, okay, is not going to hear the sonic boom. Question number 18. As a source of continuous sound approaches you at the constant speed, you will be aware of an apparent increasing of its loudness and wavelengths, loudness and frequency, frequency and wavelengths, loudness, frequency, and wavelengths. None of the above choices are correct. So this is a Doppler effect. Okay, we know that the frequency and lambda will change. Okay, but if the source is moving toward you, the frequency increase, but the frequency and wavelengths are inversely related to each other. So the wavelengths decrease. If the source is moving away from you or you moving away from the source, the frequency decrease and the wavelengths increase. Okay, so definitely, okay, so the frequency and the wavelengths will have the opposite. Okay, frequency and wave. Okay, yeah, frequency and wave, okay, are inversely related to each other. So at this situation, okay, if the frequency increase, the wavelengths decrease. If the frequency decrease, the wavelengths increase. So it means that loudness and wavelengths are not correct. Okay, so because loudness is different than the frequency, so the intensity of the wave, sorry. Okay, loudness and frequency. Yes, the loudness and frequency is the right answer. Frequency and wavelengths, they are not increasing. Just the frequency increase. Wavelengths decrease. So again, loudness increase, frequency increase, but the wavelengths decrease. Okay, so none of the above. Okay, so these are wrong. Okay, the only right answer will be loudness and frequency. Question number 19. If at a concert you run toward the orchestra, the frequency of the sound, we just said that, again, Doppler effect. When you are moving toward to the sound source, the frequency that you hear will be bigger, it means that the frequency will increase. Number 20, a sound source of high frequency emits high amplitude, no. Speed, no, because the speed is going to be constant. Okay, so pitch, yes. Okay, pitch is exactly the frequency. Again, s speed, you may say s speed is the frequency time lambda. Okay, the frequency increase, the wave, the velocity should increase. No, no, no. When frequency increase, wavelengths decrease. Okay, so keep the velocity constant. So the velocity of sound, it doesn't matter, again, if you are hearing a sound source from a source which is moving, it doesn't matter that the sound source is moving or not moving. This velocity of sound is going to be exactly the same. The velocity will not change. The frequency and wavelengths will change, okay, but the velocity will not change, okay? The velocity of source will change if it goes from one medium to another medium, okay? So let's say if it goes from, cold air to, hot air. Okay, good. In this question, okay, the right answer is the pitch. The approximate range of human hearing is between 20 hertz to 20,000 hertz. So the right answer is the first one. Okay, so you cannot hear the sound with the frequency lower than 20 hertz. You cannot hear the sound with the frequency more than 20 hertz, 20,000 hertz. Okay, in this range you can hear sound. Okay, 22. Compression and rarefaction are characteristic of, okay, transverse waves. Longitudinal wave, both longitudinal and transverse. Okay, so, and, okay, we just mentioned that what is the transverse wave and what is the longitudinal wave. Okay, you know, the sound source is an example of yeah, the longitudinal waves, okay, which we know that the rarefaction and then the compression and rarefaction happening in the sound sources, okay, so, and when it's talking about the compression and rarefaction in the sound source, it's like an air molecule, air molecule compress, stretch, okay, when it stretches, okay, so we have low pressure. When it's compresses, they have high pressure. High pressure of the sound molecule, air molecule, sorry, it's called compression. The low pressure of the air molecule, it's called rarefaction. Okay, so let me just see, I can show you with the graph of physics. Light wave, okay, so oscillation, simple harmonic. Longitudinal wave. Okay, there you go. There you go. Yes, yes, yes. Let me just show you here. So this is the example of longitudinal wave. Okay, so traveling and standing wave. Okay, so, and these are the sound source. Okay, let's say you just keep changing the pressure of the air molecule. Here, here, compression happening. When you have more pressure, the air is dense, compressed. Here you will have a low pressure. From here to here, from compression to compression is called one wavelength. Okay, let me just, see that, you see, this is the example of the longitudinal wave. Okay, so the propagation of the wave and uh, the medium direction are in the same direction. You will see that the compression keep running through the wave propagation. Okay, so if I just show, this is a standing wave. Okay, so like a standing wave, like, you have a spring and you keep compressing and stretching the spring from both sides. Okay, so it's will be example of the standing wave. Okay, so traveling wave. Okay, so it's like a sound source. The air molecule compress and rarefact. Okay, so compression and rarefaction happening. Okay, so that's why we will have a longitudinal wave. So this is an example of longitudinal wave. So sound waves cannot travel in. Okay, sound always need medium to travel. Air, if there is no air, sound cannot travel. Okay, so the right answer for this question will be vacuum. So sounds wave cannot travel in vacuum because there is no air, and mechanical waves like sounds, they need medium to be travel. A wave having a frequency of 1000 hertz vibrate at more than 1000 cycle per second, less than 1000 cycle per second, or equal 1000 cycle per second. Yeah, the 1000 cycle per second is the right answer. 25. When the speed of sound near the ground is greater than it is at higher altitude, the sound tends to be bent. Okay, at this situation, the sound bend upward. This is where the sound velocity will change. If it's going from one medium to another medium, if it's going from a cold medium, cold air to the hot air, if it's going from hot air to cold air, at this situation, okay, the velocity of sound change. So the answer is the upward. In perceiving its environment, a dolphin make use of Doppler effect. We already know what is the Doppler effect. Okay, echoes. Okay, ultrasound. Okay, the dolphin use the ultrasound as well. Okay, sending sound wave. Okay, and then they detect the reflected sound from the source, from the object, from any block. Okay, so and they analyze. It's gonna be this ultrasound. Echoes is kind of reverberation. Okay, so interference of the incident wave and the reflected one. Yeah, they do all of the above choices are correct. The wavelengths of sound that carry farther in air are relatively long. Yes, the wavelengths of the sound that carry farther. Okay, so it means that they are relatively long. Okay, so if the wavelength is bigger, okay, definitely it can carry farther in the air. The natural frequency of an object depends on its size, shape, elasticity, size and elasticity, size and shape and elasticity. Okay, so it depends on all three: size, shape, and elasticity. Some singers have been said to shatter a crystal chandelier shatter with their voice. This is a demonstration of interference and echo, resonance, bits, or sound refraction. So it is a definition of the resonance. Okay, what is the resonance? Okay, each object has its own natural frequency. Each object has its own natural frequency. Okay, so what does it mean? You know, objects, any material are created from molecules and atoms. Atoms, they have nucleus and electron, orbiting around the nucleus. Okay, you see there are vibrations, and and each one has its own vibration. Okay, so if you create a, I don't know, here is a sound. Okay, if you could create a sound that's become its frequency become equal to the frequency of the natural frequency of the crystal chandelier, you will see a vibration. Okay, so we call this phenomenon resonance. So the right answer for this question is resonance. Question 30. The phenomenon of bits result from sound interference, sound reflection, refraction, all of these, none of this. The bit result of sound interference. Okay, sometimes you have one source is radiating sound, but the sound is radiated, reach to the block, okay, and then reflected back. The interference of the incident and reflected one, okay, cause constructive interference or destructive interference. Okay, so at this situation we have a bits. So bits is the interference of a incident wave and reflected wave. Okay, so 31. In the case of radio, which has the higher frequency? Carrier wave, sound wave, neither. Both. Okay. In case of radio, okay, so again, sound wave is not a mechanical. Carrier wave will have a higher frequency. Okay. 32. A 240 hertz sound, okay, we have a frequency which is 340 hertz. Travel at this speed, okay, the speed is 340 meter per second. What is the wavelength? Okay, we know that the velocity is frequency time wavelength. Good. This is multiplication. We can rewrite this equation. We can write lambda is equal velocity divided by frequency. What is the velocity? 340 meter per second. What is the frequency? 340 hertz. Okay. So if you divide these two, okay, what would happen is going to be 1 meter. Okay, again, hertz is 1 per second. Second and second cancel each other. What is left is going to be just 1 meter. The right answer is 1 meter. Question number 33. In which one of these media does sound travel the fastest? Steam, water, water vapor, ice. We said that sound need medium to travel. If we have a medium, very dense medium, because the molecules are so close to each other, when the sound reach to the first molecule, hit the object, when it hit the first molecule, okay, if the other molecule is close to the first molecule, it will be vibrated fast. So definitely the dense material can help sound travel fast. So here, ice is more dense than water, dense than steam and water vapor. Okay, so the ice is a good option to move the sound. Okay, the bit frequency produced when a 240 hertz tuning fork and 246 hertz tuning fork are sounded together. So if we want to find the bit frequency, okay, so We have this formula, which is the bit frequency is going to be f2 minus f1, the absolute value. So we have 246 minus 240. Okay, it will create a bit frequency of 6 hertz. Okay, question 35. Any questions so far? Okay. A general rule for estimating the distance in kilometers between an observer and a lightning bolt is to count the number of seconds between seeing the lightning and hearing it and dividing it by 3. Okay, so 3 is the right answer. The pitch of musical sound depend on the sound waves, wavelengths, amplitude, frequency. Okay, as we said that the pitch, other number, other term for pitch is the frequency. Okay, so 37. The loudness of a musical sound is a measure of the sound wave speed, amplitude, wavelengths, frequency, all of this. So the loudness is always related to the amplitude, not frequency, not speed, not wavelengths. Good. The loudness is directly related to the amplitude of the. What is the amplitude? Let's say if you create a wave, displacement on time or position doesn't matter. If this is your wave, this is going to be the amplitude, the distance from the crest to the midpoint, or the distance from the trough to the midpoint, okay, is called the amplitude. Okay. Now we have a graph questions. Okay. So I would like you just listen, okay, so, and because as I said already, we have displacement over time. Sometimes we have it, the displacement of the wave, this is kind of, displacement of the wave over time. Sometimes we have displacement over position. When it is the time, it helps us to find the period. When it is a position, okay, so it helps us to find the wavelengths. Okay, here in this problem, which is question number 30, what was that? 38, okay. Your number might be different, okay, but the concept is going to be the same. We have a displacement over time. Okay, this is a perfect graph to help us to find the period. Okay, the distance between, you know, crest to crest is going to be one period time. How many crests we have? You see, 1, 2, 3. Okay, so it means that from one to another one is going to be one time period. From this to this is going to be another time period. Okay, so this graph representing 2t time, 2 period time. And the question is telling that calculate the period. Okay, from here to here is how many second? Okay, it's telling that h y-axis, okay, or the horizontal axis, which is representing the time, is changing from 0 to 190. From here to here is 190. Okay, h is 190. Okay, how many of t is 190? 2t is 190. So how I can find the period, which is time? T is gonna be 190 divided by 2. 190 divided by 2 will be 95 second. 95 second is gonna be the period time. Okay? Any question? Does make sense? Again, this graph representing two period time. What is the period? Time from one crest to another crest. Okay, it means that this is one complete motion happening. How many vibration we have here? One, two vibration. Okay, good. We can even calculate the frequency. Okay, how we can calculate the frequency? We can say 1 over 95. Or we can calculate the frequency other way. Okay, how many vibration we have? We have one, two vibration in how many second happening? 190 second. This is another way to calculate the frequency. But this question is not asking you to calculate the frequency, just the period. I'm just showing you how you can use this graph and calculate the frequency. Okay, question number what is this question? This is, what is the question number? This was 38 and this is going to be 39. It's telling that the graph above has the dimension g 4 to negative 4. Here, 4 to negative 4. And then h is changing from 0 to 100 meter. Okay, there you go, 100 meter. Okay, this one is displacement over position. From this, we can find the lambda wavelengths. Okay. Calculate the wavelengths. Okay, what is the wavelengths? The distance between two crests or the distance between two trough or the distance between, let me just use different object. Okay. Or the distance between two consecutive, from here to here. From here to here. Okay, good. So how many vibration we have? One, see, this is going to be one lambda. From this to this is going to be another lambda. This graph representing 2 lambda. And 2 lambda is how many meter? 100 meter. So what is the lambda? 100 divided by 2 is going to be 50 meter. So it means that from here to here is 50. From here to here is 50. 50 plus 50 is 100. This is how we can calculate the wavelengths. Okay, next graph. The dimension of graph above are 24 centimeter. Okay, this is 24. This is negative 24. And the y-axis is 0 to 1/22. Again, 1/22. And again, we can, because this is a time, we can calculate the period. Okay, it's telling that calculate the amplitude. Okay, we already said that what the amplitude means. Okay, the distance from the cross, okay, to the midpoint. This is amplitude. The distance from the trough, okay, to the midpoint, okay, which is going to be the amplitude. Okay, so how we can find the amplitude? We know that from here to the top is 24. This is one, and then from here to here is another one. Yes, okay, 1 2 3 block, 1 2 3 block. Okay, so it means that they are same. From here to here is 2 amplitude. Okay, so it means that amplitude is going to be 12 centimeter. Okay. So if I ask you to calculate the period, how you can calculate the period? Again, this question is not asking to calculate the period, okay, but I will show you how to calculate the period. You know, one vibration. Yes, this is going to be one time period. This is another vibration. This is going to be another period. Okay, so again, this graph shows two period time. Okay, 2t equal, what is the time? 120. T is going to be 60 second. Okay, 120 divided by 2 is going to be 60 second. Okay, so next one. Again, G is 20 to negative 20, 20 to negative 20, and it's telling that H is from here to here is 20 second. Calculate the frequency. Okay, frequency definition is 1 over period. We need to find the period from here, yes? Okay, because these can help us to find the period because this is displacement over time. We say from here to here is one period time. From here to here is another period time. These wave representing two period time. So 1t, 2t. 2t is equal how many second? 20 second. T is going to be 20 divided by 2, which is 10 second. So it means that this is 10 second, this is 10 second. Together is going to be 20 second. This is the period. What is asking to find the frequency? 1 over 20 is going to be our frequency. Okay, if I divide 1 by 20, it will be 0.05 hertz. 0.05 hertz. Okay, good. So what is the next one? I believe this is the last one. Okay, so again, this is a displacement over time. Again, time. This can help us to find the period and the frequency. It's telling that if y-axis, so yeah, sorry, y-axis G is from 8 to 8, okay, and then x-axis, okay, it is 80, okay, from here to here is 80. And if the wavelength is given, the wavelength is 170 meter. Okay, calculate the speed of this wave. Okay, what is the speed? How we can calculate the speed? The speed formula, look at the formula, is frequency multiplied by lambda. I have lambda, I don't have frequency. It means that this question is asking me use this graph and find the frequency. Okay, I can find the frequency because this is displacement with respect to the time. Time can help me to find the period. Okay, so from here to here is one complete vibration. This is 1t. From here to here is another complete vibration, is another t. Okay, again, this graph representing two period time. 1t, another t is going to be 2t. Is how many second from here to here? Is 80 second. So t is going to be 80 divided by 2, which will be 40 second. Okay, but I need frequency. Okay, that's good. Frequency is 1 over t, 1 over 40. Okay, so now I have frequency. Okay, now the frequency is now. I can plug it here. 1 over 40 multiplied by, what is the lambda? 170 meter. So what would be the velocity? 170 divided by 40. If I round it, it's still in round to do two decimal places. Okay, 170 divided by 170 divided by 40 is going to be 4.25 meter per second. 4.25 meter per second. Okay, so we are done with the multiple choice. What we have one more to do, one more thing to do. Okay, we still have 30 minutes. How do you do the amplitude? Okay, amplitude, okay, again here, if I want to find the amplitude for this one, the amplitude is distance from the midpoint, okay, to the point, to the trough or to the crest. Good? So if I want to find the amplitude here, let's say, from here to here is 8. How many block I have? 1, 2, 3, 4. It means that each block representing 2 centimeter, yes? How many block representing the amplitude? 1 block, 2 block, 3 block. Okay, so the amplitude here is going to be 6 centimeter. This is amplitude, but this question is not asking you to calculate the amplitude, okay? So just the velocity. Okay, so, okay, we are not done yet, okay? So you are welcome. There is one more practice review, okay? So, and I would like to go over that practice review with you, okay? So let me just, stop recording for now. Okay. Okay, this is the second part, the second practice review, okay? So it's the graph problems. So, and the first question is an example of the standing wave. And I would like to explain the standing wave first, okay, and then come back to this problem because we need to know what is the standing wave, okay? So, and when I explain the standing wave, okay, we can come back and then solve this problem. So, in the chat box, okay, so can you please tell me how many of you know about the standing wave? Okay. If the answer is yes, put yes. Okay. If the answer is no, put no. How many of you have a good understanding of standing waves? Okay, so good. Okay, so I will try to explain then. Yeah, I will definitely go over the standing wave. Okay, so let me just open the whiteboard. I'm gonna open the whiteboard. Okay, so format background. Okay. Let me just make sure that it is recording. Yes, it is being recorded. So, I want to explain what is this standing wave. Let's say there is a person, okay? And this person has a string with the length of L, and one end of this string is connected to the wall. This person try to move this string up and down. What exactly happened? Okay, so the wave start moving, yes. The wave will be created. You can just try this at home, okay? So the wave will be created, okay, and reach to the wall. This is called incident wave. What happened when it hit the wall? Two things happen. One, because this is carrying energy, yes? Some portion of energy will be transferred to the wall and some portion will be reflected back. So what does it mean? It means that when it's the wave hit the wall, It cannot go through the wall, okay? It will be reflected back. It will be reflected back, okay? This is called reflected wave. Okay, now how many source of wave we have here? The incident, the person is one source, yes? Okay, the person is one source which is creating a wave. Now, when the wall doesn't let this wave to go through it, the wall will be acting as a second source of the wave, you know? It's reflecting the wave. It means that the wall itself is radiating a wave, okay? Now we have two sources, a person and the wall. And both of them are creating waves. Make sense? The person is creating an incident wave. It cannot pass through the wall. The wall reflect that wave, and the wall, you see that is acting like a wave, the source wave. Now we have two source of waves, and we have a superposition law. Okay, superposition law is telling that if you have more than two waves, these waves can add, can cancel or add each other. Let's say if you have one wave like this and then another wave like this, you know, you can add these two waves, you know, amplitude, you know, here, you know, they are in the same phase. When you add these two waves, it's going to be a wave with a bigger wavelengths. Good? With a, sorry, with a bigger amplitude, you know. Let's say this is A, this is A. Now this is going to be 2A. We call this constructive interference. Sometimes we have wave, two sound wave, okay, but they are exactly at different phase. This is, this one has its max, this one has lowest value, okay? So we call this positive A, this is negative A. When you add these two, by adding, again, by using the superposition law, okay, we are adding these two. When you add these two, they cancel each other and there will be no wave. This is called destructive interference. Okay, okay. You remember I said we have two wave here when the person is start, you know, moving the string up and down, okay. It's create the incident wave, the wall reflected back, okay, so there will be two wave, and these two sometime at sometime they cancel each other. So when these happen, it depends on the frequency. Sometime we will have this wave. This is called a standing wave. Definitely you have seen in the experiment. Sometime we will have this kind of wave. You know, we have one loop, yes? We have one, two, you know, one and one, okay, two loops. Sometime we have three loop. Sometime we have four loop and five loop. Okay, this person can create all of these situation. You can try at home, okay? So it is a good experiment. Okay, let's have a string attached to the wall. Try to create this one. When you create this one, it means that you are creating a standing wave in the first harmonic. Okay, you can calculate your frequency. How? Let's say how many times you are moving your hand up and down, or up and down. Good. And then record the time. The number of vibration over time give you the frequency. And then you can calculate the frequency of the fundamental. Okay, this is going to be the first fundamental frequency. This is the second harmonic because we have two wave. you will see two loops are created. This is the second harmonic. This is the third harmonic. This is the fourth harmonic. Good? Fifth harmonic, third harmonic. Let's say if you calculate the harmonic for the first one, let's say this is a F1. You can try it at home. Okay, so if you double the first harmonic, you can create the second harmonic. If you triple these, you can get the frequency, the third harmonic. If you quadruple the first harmonic, okay, you can get the frequency of the fourth harmonic. So the fourth harmonic is going to be 4 times F1. The frequency of the third harmonic is going to be 3 times of F1. The frequency of the second harmonic is going to be 2 times F1. Good? Okay. Let me just erase these. And this is just F1, yes? Double the first fundamental frequency, you get the second harmonic. If you triple the first harmonic, okay, you get the third harmonic. Good? And what are these points? These are when the destructive interference happening. These points when the constructive interference happening. I just kind of explain what does those means. Okay. Again, this is destructive interference. These are constructive interference. This is where destructive interference happening. This is where constructive interference happening. This is where destructive interference happening. Yes, this is constructive interference happening. We call these antinode. These are nodes. In the first harmonic, we have two nodes and one antinodes. In the second harmonic, we have one, two, three nodes and two antinodes. In the third harmonic, we have one, two, three, four nodes and then three antinodes. And then the same for all. How can I calculate the wavelengths? You remember I said that the length of this string, let's say the length of this string is L. Okay, the string length was L. How can I find the wavelengths to see how many meters? Okay, let's say this L is 1 meter, yes? How can I find the wavelength? You remember we said that wavelength is one complete motion, yes? From the from this two consecutive point, okay? Okay, one complete, okay, is the one wavelength. Half of this is half wavelengths, good? Half wavelengths is gonna be one wavelength. You see a half a loop, good? This is a half a wavelength. Here in the second harmonic, each one of these is half a wavelength. In the third harmonic, each one of these are half a wavelength. Each one of these are half a wavelength, yes? Okay. In the first harmonic, how many half a wavelengths I have? I have one half a wavelength, which is equal to the length of the string. How can I find the lambda here? Multiply by both sides by 2, yes? By 2. So half wavelength is going to be 2L. Again, this is 1L, yes? In the second harmonic, how many wavelengths I have? One half length, half wavelengths, two half wavelengths. Two half wavelengths is going to be L. There you go. 2 and 2 cancel each other. The second harmonic wavelength is going to be exactly equal L. You see? The first harmonic, the wavelength was 2L. The second harmonic, the wavelengths become L. How about the third harmonic? How many wavelengths I have? Half a wavelengths I have. There you go. I have 3 half a wavelengths is equal to what? The length. How can I solve this? By lambda, just multiply both sides by 2/3. So it means that the wavelength of the third harmonic is going to be 2L divided by 3. I don't want you to memorize the formula. I want you to know what is the first harmonic, second harmonic, third harmonic, okay? And then from there you can calculate the wavelengths by your own. So in the fourth harmonic, how many wavelengths I have? Yeah, 1, 2, 3, 4. 4 half a wavelength is going to be, again, this is the length of the string, yes? Length of the string. Good? So, and this is going to be 2 lambda equal L. So lambda is going to be L divided by 2. There you go. Force is going to be L divided by 2. Again, I can give you formula. Okay, so again, what is the formula? The frequency of the n harmonic is going to be n times the first harmonic. The wavelength of the n harmonic, okay, is going to be 2L divided by n. So these are the two formula that you can memorize, okay? But again, you don't need to memorize, okay, as long as you know what exactly happening here, yes? Okay, but again, just in case if you want to memorize the formula, these are the formula. For instance, again, if I want to find the wavelengths of the fifth harmonic, yes, fifth harmonic is going to be 2L divided by 5. If I want to calculate the wavelengths of the fourth harmonic is going to be 2L divided by 4. Okay, 2L divided by 4 is going to be L over 2. You remember? We just calculated L over 2. The wavelengths of the, what? The wavelengths of the third harmonic, yes, is going to be 2L divided by 3. And L is going to be the length of the string. If you remember, we just said that the length of a string was 1 meter, yes? If it is a 1 meter, okay, so you can just need to plug for L1. Okay, this is going to be 1 over 2 is going to be 0.5 meter. The wavelength of the fourth harmonic. The wavelength of the fifth harmonic is going to be 2 times 1 divided by 5 is going to be 0.4 meter. And then 2 times 1 divided by 3 is going to be almost, 0.67 meter, the wavelength of the third harmonic. Good? Any question? Does make sense? Again, you can re-watch this video, okay? So again, I think it will be helpful. Okay, let's go back. Okay, let me just do one example, okay, and then we can go back and solve that problem. Again, we have this person, okay, and this person has a rope with the length of 4 meter. Okay, and this is attached to the wall. And the person need a frequency of 10 hertz to create first fundamental. This is a fundamental frequency. Good. We call this, okay. What is the wavelength here? Wavelength is 2L divided by n, yes? 2L divided by 1, the first fundamental. Okay, I can calculate 2 times 4 divided by 1, okay, 8 meter. So lambda 1 is going to be 8 meter. I asked to calculate the velocity. Velocity is going to be frequency multiplied by lambda. 10 times 8 is going to be 80 meter per second. Now, I ask you, what is the frequency of the second harmonic? What does it mean, second harmonic? It means that instead of one loop, you have two loop. Okay. You remember we said F2 is 2 times F1. Okay. Or Fn equal n times F1. Now we are in the second harmonic. 2 times, what is the F1? 10. 2 times 10 is going to be 20 hertz. Yes? What is the lambda? Lambda 2 is 2L divided by 2. Yes? Again, instead of n, I plug 2. Or we can say half a lambda plus half a lambda. Half a lambda plus half a lambda is going to be 1 lambda. 1 lambda is equal to L. Any way that you are comfortable. Or you can use the formula. 2L divided by 2 is going to be L. What was the L? 4 meter. Okay, I asked you to calculate the velocity. The velocity is going to be, again, what is the frequency? 20. What is the wavelength? 4. 20 times 4 is 80 meter per second. I found something. It doesn't matter what frequency you are, what harmonic you are. Your standing wave velocity is always same because the medium is exactly the same medium. Medium has not changed. Good? If I ask you to calculate the third harmonic, frequency, wavelengths, and velocity. Okay, there you go. 1, 2, 3. 1, 2, 3. Good. Half a lambda, half a lambda, half a lambda. Okay, again, if you don't want to use this, okay, you can use the formula. The frequency, the third harmonic, is going to be 3 times of the first frequency. 3 times F1 is 10. It's going to be 30 hertz. What is the lambda? Lambda 3 is going to be 2L divided by 3. Yes? What is the L? L, it is 4. 2 times 4, 8. 8 divided by 3. 8 divided by 3. 8 divided by 3 is 2.7 meter. 2.7 meter. Good? Okay. So again, if I calculate the velocity, so I can just plug it here. Okay, 30 times 8 divided by 3. Okay, if I just say, okay, I don't use the decimal, it's going to be 2 times 4, 8. 8 divided by 3. 8 divided by 3. Okay, if you simplify, this is going to be 80 meter per second. Again, you see, first harmonic, second harmonic, third harmonic, the velocity is same, but the frequency and wavelength will be different. Any questions so far? Does make sense? If the answer is yes, please put the yes in the chat. If it is confusing, put confusing in the chat. Okay. Again, you can rewatch this video. Okay. So, I will send you the recorded session. Okay. Just send me an email. I will send the recorded session just in case if you need, to rewatch it. Okay. Go back to the problem. Okay. Now we are in this problem. Okay. First of all, tell me which harmonic this is. 1 loop, 2 loop. Okay. This is a second harmonic. There you go. That's it. Below is a standing wave. It's being vibrated. Okay. 80 hertz. It means that F2 is 80 hertz. That's it. What is the harmonic is vibrating? Second. What is the wavelength of this harmonic? Okay. Wavelength is going to be 2L divided by N. 2L. What is the L? L is from here to here. Yes? L is 30 meter. 2 times 30 divided how many? Which one? Which harmonic it is? The second harmonic. 2 times 30, 60. 60 divided by 2 is going to be 30. So the wavelength of this harmonic is 60 meter. What is the S speed of this? Okay, there you go. S speed, we just need to just multiply the frequency of that harmonic with the wavelengths of that harmonic. Okay, what is the frequency? 80. What is the wavelength? 30. 30 times 80 is going to be 2400 meter per second. Okay, part D is telling that what is the fundamental or first frequency. Okay, so it's telling that when it was like this, yes, what would be the frequency when we have just one loop? You remember we said that Fn is going to be n times F1. So F1 is going to be F of n divided by n. Okay, we already have the second harmonic frequency, yes? Divided by what? 2. What is the second harmonic? 80. 80 divided by 2 is going to be 40 hertz. And it makes sense. If you divide 80 by 2, it's going to be 40. So we have 40 for the first harmonic, time by 2 is going to be 80 for the second harmonic, time by 3 is going to be 120, is going to be for the frequency of the third harmonic, time by 4 is going to be 160, is going to be the frequency of the fourth harmonic, and then vice versa. Okay? And it's telling that part E, what is the wavelengths of the first harmonic? Okay, again, we can use the formula. Let me just, okay, I'll do the E here. The wavelengths of the, yes, again, lambda n is going to be 2L divided by n. Lambda 1, 2L divided by 1. 2, what is the L? L is the length, okay, which is 30. Divided by 1 is going to be 60 meter, okay? There you go. The wavelengths of the harmonic, the first harmonic is 60 meter. What is the amplitude of this wave? Okay, what is the amplitude? Okay, let me just erase here. The amplitude is, let me just change the color. Okay, distance from here to here. What is the amplitude? It is 10 centimeter. Good. That's it. Now, next question. And then we are done for today. There are two diagrams below, one with respect to the time, okay, and there you go. This is a respect to the time, displacement over time, which can help me to find the period and frequency. And then, and the other one with respect to the distance. Okay, this one is respect to the displacement over distance, which is help me to find the wavelength. Okay, let's see what we are trying to calculate. Give the value of the period. Which one I can use to calculate the period? Definitely displacement with respect to the time, yes? The first one. Okay. And from here to here is 45, yes? And we know that one complete motion is here to here is one complete motion, or is from here to here. Anyone that you help you to find out, okay, that's perfectly fine. Okay, I use this one because it is start from 0 and it's end exactly at 30. Good. Okay, the time, the period is 30 seconds. So A is 30 seconds. Give the value of the wavelengths. Okay, I cannot use to use the first one to find the wavelengths. Okay, I'll move to the next one. Okay, there you go. The wavelengths is the distance from crest to crest. Oh, there you go. This one is 30 as well. Okay, and what 30 meter? Lambda is 30 meter. The first one was 30 seconds. So B is gonna be lambda equal 30 meter. Give the amplitude. Amplitude. It doesn't matter which one you use. You can use both to find the amplitude. Because what is the amplitude? The amplitude is distance from the crest to the midpoint. The distance from, again, crest or trough to the midpoint. Okay, from here to here, yes? And at both situations, A is 10. Here, A is 10 centimeter. Okay, good. So A is going to be 10 centimeter. Find the frequency. Okay, what is the frequency? Frequency is 1 over t. We already have t. Okay, it's going to be 1 over 30. Find the velocity. Okay, what is the velocity? Velocity is frequency multiplied by lambda. Good. We have frequency, which is 1 over 30. We have a lambda, yes, which is 30. Okay, 30 and 30 cancel each other. It's going to be 1 meter per second. Okay, good. F and G is telling that draw a wave on the first diagram that completely cancel the wave. Okay, so let me just erase this. It's telling that draw a wave that cancel this wave. Okay, it means that they should be in the opposite phase, yes? If I want to draw, okay, it should be, something like this, Good. When you add these, okay, they kind of cancel each other, positive amplitude, negative amplitude, they cancel each other. Okay, this is going to be, they cancel each other. G. G is telling draw a wave on the second diagram that completely constructive. Okay, completely constructive, it means that, let me just erase this. Completely constructive, it means that the wave should be exactly at the same phase. Okay, same phase. I can completely draw, exactly at the same. Good. These make the wave completely constructive. Okay, so let me just start recording.